So capacitance and magnet review questions. Storage of electric charge in a capacitor is often linked to storage of water in a vessel. Charge capacitor is similar to a vessel holding water. It's holding charge. So to complete this analogy, relating the electrical quantities of charge, voltage, and capacitance to the quantities of water, height, and volume. So as you go to review this, vessel dimensions, quantities of charge and voltage. So let's say Christian.
Yep.
Water height.
I never got to this one. Let me see. Complete this analogy. I never got the answer to this one, even reading through the e version of the book, the water analogy.
All right. So we did this back in week 11. And I think that, you know, if we're now week 16, ask me some questions because there's like a month in between. And I also apologize. We've been doing so many things that we didn't review this earlier. But let's help you out with this. So the height of the water would be analogous to the amount of charge. Okay. Measured.
The voltage would be the height of the water, right?
Yeah, so the height would be similar to the amount of charge, which is measured as Q in coulombs. And here,
kind of acting like a capacitor.
Well, this is asking you how the capacitor is acting, like if you would compare it to a vessel holding water. So 1 coulomb of charge is equal to 6.25 times 10 to the power of 18 electrons. This was similar to 6.25 billion electrons. A whole lot of electrons for 1 coulomb. So we would measure the water height would be the amount of charge, and we measure charge in terms of a unit we call coulombs. And then your water volume would be equal to capacitance, which is equal to the ability to store charge. And the vessel dimensions would be similar to billion. Did I spell something wrong? Billion. Water volume. The ability to store charge. Vessel dimensions. Let's actually change this. Water volume would be to voltage. Ability to store charge. Measured also in volts. And your vessel dimensions would be most analogous to capacitance, which is the ability to store charge based on several things, based on surface area of plates, distance between plates, and dielectric materials. So we talked about this in when we had our capacitance lecture some time ago, and if we refer back to, let's see, we can go ahead and save this guy and close this guy out. Dope. And we come to here, and we go to our friend right here, and YouTube. Okay, so while that's coming up, so we would go ahead and answer this question on this basis of those. So let's go ahead and bring in this guy, YouTube, and go to channel, my channel, and then go to the Kogai videos. And in the Kogai videos, you'll find a lot of these answers will appear here. There was a discussion about capacitors, how to read the values. That was one area that we had discussed capacitors. And so that would be one place to look for that. We won't be reviewing this, but that's where you would have some of the answers pertaining to where they're similar to, okay? Now, it says here, how are electrolytic capacitors constructed? What is particularly noteworthy about their use? So, who would like to try this? Andrew, you want to try this? How do we construct electrolytic capacitors? How are capacitors constructed, first of all, and how are electrolytic capacitors constructed?
I'm not too sure.
I had put
yes, good. Yes.
Negative terminal, and they're sensitive to their polarity.
Oh, there you go. Very good. So first of all, capacitors are conductive plates separated by special insulators called dielectrics. Second, dielectrics, the dielectrics equals insulators used in the construction of capacitors. Dielectrics used for caps include, so who remembers what they include? No, rubber is an insulator, glass is an insulator, wood is an insulator, but we don't use those materials to make capacitors. What do you recall of the materials we used to make capacitors?
Paper, air.
Paper is one, air is another.
Ceramic.
Ceramics, okay, all different kinds of ceramics. Plastics. Yeah, so these would be plastics, and in particular for this particular question, and electrolytic paste compounds. Okay, electrolytic paste compounds. This would be similar to the old carbon batteries. If you remember the cheapy batteries that you might find at your dollar store that are not alkaline, well, gosh, if they're not alkaline, there would probably be the super duper version, and the super duper version not classified as alkaline are probably the cheap carbon batteries. And why don't we use cheap carbon batteries in our expensive electronics anymore? Because when they get old, what do?
Corrode.
Can leak. Corrosive materials when aged. Okay, yeah, so they do corrode. And so what they do is they leak this corrosive materials when they age. But what are that's what happens with carbon batteries. And how are they built? They're made with electrolytic paste compounds. It is a paste. And so the construction of an electrolytic capacitor is that they're using this paste material. And third, yes, you're correct, electrolytic caps are polarized and will explode if connected voltage is reversed. Probably put an exclamation on that. They will explode. Very exciting when that happens. When we meet back together, during the first week of June, when we come back into lab together, because we have some that we're not only going to bring our equipment back, but also finish up on some of these things, will somebody remind me? We want to blow up a capacitor. How many of you remember the demonstration where I discharged a charged capacitor with a screwdriver?
Yeah, I remember that.
Yeah, you remember that because that was a big spark, yeah?
Yeah.
Okay, we didn't explode that particular guy because if I exploded a capacitor of that size, I would have no arm left, okay, because that thing will explode almost like a hand grenade. But we will gladly explode a small capacitor, and we'll have fun doing that by reversing the polarity. So as it says, how are electrolytics constructed? What is particularly noteworthy about their use? First of all capacitors are conductor plates that are separated by special insulators known as what? What word did I use at the end of the sentence?
Dielectrics.
Dielectrics. Okay, so dielectrics is a special kind of insulator. Dielectrics right here are insulators used in the construction of caps. Dielectrics include air, ceramic, paper, plastics, electrolytic paste. And electrolytic caps are what? Polarized, and they will explode if reversed. Are we good with this? So far, so good. Okay, right here. Capacitors may pose an electric shock hazard, even in unpowered circuits. Why? What do you think, Mr. Lau? Do you remember?
No.
Well, were you there for the demonstration where I put the screwdriver across the terminals of the capacitor? Were you there that day when I did that demonstration? That's a yes or no. Lau guy.
Short answer. Think about maybe it's a yes. Almost.
All right, so caps can pose an electric shock hazard because they can hold a charge for quite some time, even after the power to it has been disconnected. Okay, that's what the purpose of that demonstration was. I charged up a capacitor, and then I took away the power, and then I discharged it, and it showed a very, very impressive spark. If that was your hand, then your hand would have been burned. That's why it poses an electric shock hazard, even when it's unpowered. And this is the reason why. Okay. Let's see. It says here. So this particular question takes us over into the next page. So I'm going to just move this question over to the next page. So we can see it all on one page. Okay, very large capacitors, typically in excess of 1 farad, often used in DC power wiring of high power amplifier systems installed in automobiles. Capacitors are connected in parallel with the amplifier's DC power as close to the amplifier as possible, like this. Okay, what is the purpose of having the capacitor connected in parallel to the amplifier's terminals, and what is the benefit does this give to the audio system? And if I remember correctly, I think Kyle or Andrew gave me a pretty good answer on this. Remember what your answer was?
I answered it as a car radio system, because that's all I know is the grounding out of all that and the way that it hooks up for the subs and stuff.
Yeah, what's it do for the subs?
It helps keep the power so that it doesn't drain your battery and your alternator and stuff. We know when you're playing your music really loud.
Right on the money. You hit it right on the money. So it helps base frequencies when car stereo system is being played loudly so that the battery will not be drained during those high amplitude volumes are being played. Anybody else? It's good. All right, now you've got capacitors that are connected in series with each other. How do you calculate capacitance total in series? So CT in series calculates how? Question goes to Pauline.
The capacitance, the formula would be on capacitor. It would be, oh, that's a good one. It would be
Do we add
what
them?
I did. Yeah, what I did is I did the 1/33. Was that microfarads?
Yeah,
Plus
there's a name for that
1
formula.
over 33.
You're right. You're right.
Microfarads.
Yes. So we use what formula? It's called the, look at my screen.
It's called the, I can't see your screen because it's reciprocal. I knew it.
There you go. It's called the reciprocal formula. I'm trying to make it bigger here for you. Is that big enough for all of us?
Yes, thank you.
Okay, so we're going to use this thing called the reciprocal formula. All right. So CT in this particular case, CT is going to be equal to 1 over 33 microfarad plus 1 over 33 microfarad. Let me get some space in here. So 1 over, open parentheses. Okay. So there's your formula. It's 1 over the reciprocal of 33 microfarads plus the reciprocal of 33 microfarads. And so the answer is going to be
16.5 microfarads.
16.5 microfarads. Okay, everybody should be able to do that on their calculators and end up with that value. And yeah, you're going to see this, something similar to this. All right. Next is a graph capacitor voltage and capacitor current over time when the switch is closed. So we've done this when we looked at time constants, remember? So when we go to our YouTube videos, and this is a capacitor with a voltage. So we have a capacitor, DC voltage source, and resistor. So what it is you're going to be looking at as a refresher would be right here, RC time constants.
Time constant.
See, RC time constants. So in RC time constants, we were able to demonstrate, move this along, move this along, move this along, move this along, and right about in here. Okay, we continue a little further, a little further, a little further, and somewhere here. So this is how your voltage works. Your voltage starts at nothing, and then it charges up to a maximum. That's how the curve should work for voltage. And if we go along further in our video, we should see how current behaves. And current should start off as maximum and go down to 0. So the green curve represents the voltage coming up from 0 time all the way up to 5 time constants. It reaches maximum. And the current starts at maximum and over 5 time constants goes to 0. This is how this particular graph should be drawn, all right? So if I were to do this, let's see, do I have a pick of colors? Galaxy? No, I don't know galaxy. Okay, I'm going to show current. And current will start here and gradually go out like so. So this will be your I, C. And, whoops, come back here. And then insert, draw. And I don't have green. But let's see, I will pick green. So here's green. Now that being said, the voltage here will start at nothing and behave. Oh, this is a sad drawing. It's hard to do with the mouse. So this will be your VC. Okay, so it starts at 0 and ends up in max. So VC equals max after, oh, this is hard to do with the mouse. After five, oh, this is so sad. I'm sorry for how horrible this looks. After 5 tau. And then your IC equals minimum after 5 tau. So what comes first? Which one comes first? Does voltage reach maximum first or does current reach maximum first? What are we going to say about this?
Current reaches maximum first.
So therefore we have ice. Remember ice, Eli the Iceman. And why is ice pertinent in this particular circuit? Because C stands for a capacitor. Okay, C stands for the cap. And we happen to have a cap in this circuit. And in a cap circuit, when we look at these curves, current is at maximum, red up here, and before voltage reaches maximum at the end of 5 time constants. So this is the thing to remember, and this is what your curves should look like for number 6. Any questions on this for number 6? Okay, number 7. What is the value of resistor that is needed to be connected in series with a 33 microfarad capacitor to provide a time constant T of 10 seconds? So let's go ahead and let me hit escape, get out of here. ohm. All right. So let's go ahead here. Rolando, you want to help us out with this?
Only resistor. No.
Okay, so tau is time constant, and that's equal to the amount of time for a cap to charge or discharge 63.2% of the remaining value. Tau is tau equals R times C. So do we have a formula for tau? Tau is equal to R times C. What are we looking for? We happen to have the C value.
Yeah.
We happen to have the time. We're looking for is the value of the resistor, yeah? So how do I switch this around in order to get R? R is going to be equal to
Tau divided by C.
divided by C. All right, so we're just going to do some basic transposition here. We're going to move the C from this side of the, we're going to move the R from this side of the equation to the other side. And so we would do this, we can move the C to the other side. And so if this is a multiplication function, then it would become divide on the other side. That's how we end up with this. Let me change this to lowercase t. And then, so R is going to be equal to, what do we have here? 10 seconds. And that's going to be divided by 33 microfarads.
So I got the answer is 303.03 kilo ohms.
Okay, so hit me with that R value again. It was what?
303.03.
Yes.
103?
Yes. Divide by 33. So 303.03
kilo
ohms. Okay, mathematically, that is what you should get, and that's how you calculate this value. Any questions there? Okay. Here, you're asked for some magnetic information, and so you need to draw the magnetic flux lines extending from this bar magnet. What would the flux lines appear like? So they would appear something like this. Let's go ahead here. And they would appear, okay, pardon my mouse. Starts from here, comes out, and goes back over here. And the arrows are drawn this way. They would be coming out here and over to here. And the arrows are this way. So your flux lines are drawn from the north to the south. Here's another one here. Like so. Are we good with this? That's what you need to demonstrate for number 9. Number 10. Let me go ahead, escape. All right. So for number 10, mechanic visits you one day carrying a large wrench. She says the wrench became magnetized after setting it near a large magnet. Now the wrench has become an annoyance, attracting all of the tools in her toolbox. Can you think of a way to demagnetize the wrench for her. Okay. So, Andrew, what do you think?
I just told my brother this is the one that I had I didn't understand. I didn't know how to do this one.
Well, let's think about your toolbox. Do you happen to have any tools in there, like a screwdriver,
I know
that
how
is
to
magnetized?
I mean, you take it to the back of the speaker or whatever with the magnet, and then it'll magnetize it. I just don't know how to demagnetize it.
Okay. All right. All right. Well, you've experienced a real life situation where, yeah, it's very true. You take that screwdriver and you happen to have it near the back of a speaker, and boom, you've magnetized the screwdriver. Now the screwdriver nicely, maybe intentionally, because you chose to magnetize it, is now a very handy device because it's picking up screws for you and can hold the screw in place. So that's why a lot of people like to have magnetized tools, is to, in the case of a screwdriver, a Phillips or a blade, you put the screw at the end of the screwdriver and it holds it in place magnetically. So that's a good thing. Here we have a mechanic and she's got a wrench, and the wrench has become magnetized. Now, you don't want a magnetized wrench because all kinds of tools are sticking to it. So we can demagnetize any accidentally magnetized tool by, who wants to try this? One way.
I had to like Google this one because this is very
Googling is
interesting.
fine.
Yeah,
What did you find out?
Well, in all of the things that I've seen, there's 4 that I've actually answered on this one. One is to rough handle it, where I guess you're just going to bang the wrench. 2 would be heating it, which
Wait,
that's
let's
amazing.
let's do one at a time. Bang the wrench
Right, bang the wrench.
to demagnetize it. That's correct. Demagnetize it. Second way is
Heating.
apply heat to demagnetize it. That would be good. It.
Leave it alone for a long time.
It'd have to be an awful long time. What's another way? What else did you find out in Google?
Passing electricity was another one.
Passing electricity in the opposite
Right, in the opposite direction.
polarity to demagnetize it. What else did you find?
How would you do number 3, like in person, like on a wrench?
You could hook it up to a battery, depending upon which side is north, and you can determine which side is north based on a regular magnet. So you get a regular bar magnet, and let's say that wrench was polarized north to south from the head to the handle. It was polarized north at the head, and then south at the handle. You determine this very easily with a bar magnet. So which end of the bar is attracted, so you know its polarity. And so what you do is you would attach a battery to this with wires on the handle and then on the head side. Now this better not be your car battery because you're going to short out your car battery. All right, so you can do this with something smaller. Generally, a 9-volt battery would be a good thing to start. You're going to sacrifice the battery, but the battery is going to be gone. But at least it's not likely to explode. All right, so I would recommend probably a resistor in that as well. So you don't want to hook up the battery directly without some kind of resistor to limit the amount of current. But passing electricity through of the opposite polarity can demagnetize it, just like putting polarity through a device can magnetize it. If we reverse the polarity, we can demagnetize it. So that's how you would do that. Did that answer your question, Andrew? It's a good question. I like that.
I guess that answered it. Thank you.
Yeah. And Pauline, what was another way that you discovered? You said you found 4?
Yeah, the last one was induction. That I cannot, if you can explain that.
Yeah, induction is using another magnet. Okay. with current. So you can, it's not dissimilar to number 3. Number 3 says we're going to pass electricity directly through it. And induction, use induction means wrap wrench with wire, wrap wrench tightly throughout its length with wire carrying electricity in the opposite, carrying electricity, carrying, here, let's be more specific, carrying DC to produce an electric field, to produce a magnetic field, to, and here's the word, neutralize the initial magnetic field. Okay, and so this is what can happen. You can take a screwdriver, no magnets. Okay, let's say you have a screwdriver and it has no magnets whatsoever. And then we're going to wrap wires around that screwdriver. So let's go ahead and do this for just 1 second here. Let's stop the share for a moment. Let's put out the camera. Okay, so here's the camera. And like so, move this out of the way. All right, and I have a screwdriver. Right here is a screwdriver. And what I'm going to do with said screwdriver is I'm going to use wire. So now I have wire, and I'm going to wrap wire around the screwdriver. Loop, 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 loop. And I got to make consecutive loops, nice and tight, 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 consistent size loops, consistent spacing between the loops, like so. So now, do I have loops around this particular screwdriver? And I've got both ends of my wires hanging out here, yes? So what I'm going to do, what I can do is I can hook up a 9-volt battery to the ends of this wire. So I can hook up one end to positive, the other end to negative. And as I'm passing current through this wire, there will be an electrical, there will be a magnetic field that's generated around this wire. That's the property known as induction. Induction is the property of a magnetic field being generated around a wire that has electricity passing through it. So if I have both of these ends hooked up to a 9-volt battery, there will be electricity going in through one side and coming out the other side. As these electrons are flowing, a magnetic field will be developed around this wire. Now, I concentrate the magnetic field by making these coils. Remember, we had talked about how an inductor was made. So I am making an inductor. But what I'm doing is the core of my inductor is not air. The core of my inductor is the shaft of this screwdriver. So when I concentrate the magnetic field with this coil of wires, I am concentrating a magnetic field onto this core, which happens to be steel or some kind of ferrous material, iron type material, and it will become magnetized. So I can create what's known as an electromagnet simply by putting electricity on wires wrapped around a core. Now, the most practical application of this, my friends, is this. Those of you who live in your homes that happen to have a doorbell. Not everybody uses a doorbell. Some apartment buildings use door knockers, places use doorbells, buzzers, things of that sort. Well, guess what? When they're pushing the button to the door buzzer or doorbell, they're completing an electric circuit. That electric circuit takes current and it goes in one wire through a loop of wires like this and out the other side, completing the circuit. So what happens is when you push the doorbell button, it creates a magnetic field in this coil. And since this shaft in the doorbell is not fixed, the shaft can move back and forth. It's mounted on a spring. So when this energizes, it forces the core to come in one direction, hitting the chime of your doorbell. It goes ding. And then a moment later, the spring pulls it back to hit the chime on the other side, dong. So when somebody presses the doorbell button, it goes ding dong. Because what they're doing is by creating the magnetic field on here, it forces the plunger to come out in one direction, hitting one bell, and the spring returns it in the other direction of an equal but opposite force, hitting the second bell. And because these two bells are two different frequencies of tone, you hear a ding dong, ding dong. You've never thought about that, but that's how your doorbell works. So your doorbell works by the property known as induction and electromagnetic fields onto a solid object. So if we apply this to a fixed object like your screwdriver will become magnetized through electromagnetic induction. So because we can magnetize a screwdriver this way, how can we demagnetize it? Well, we can take the same coil that we use to magnetize it, take the screwdriver out and shove it in the other direction, and the electrons and the magnetic field will demagnetize that. So that's how we explain number 4, Pauline. Number 4, we're using induction to magnetize it, and we can also use induction to demagnetize the screwdriver. Does that help answer your understanding for number 4?
Yes.
Cool beans. I appreciate the question. Everybody else understand what I was saying about number 4 and how your doorbell works? Your doorbell works by the property known as induction. And right there is your coil. And I don't have my 9-volt battery, but it's easy enough to hopefully picture with the explanation that I gave. All right, now we will go ahead and return back to share screen. And that completes these questions for number 9. Number 10. Okay, cool. It says here, large audio speaker can serve to demonstrate both principles of electromagnetism and electromagnetic induction. Explain how this may be done. All right. The same way that coil of wires works is the same way that your speaker works. And if I happen to have, let's see if I happen to have a nice image of a cross section of a speaker. Okay, so loud speaker construction. Cool. I think this is, there's several images that are really good here. This is a good image. Let's go ahead and start with this guy. So as I look at a loudspeaker, this is what many of you have in headphones on a smaller scale, in your car stereos, in your home stereo speakers. You have a speaker, and typically the big guy, there's a cone of some sort. There's a surround, which is the rubber thing that goes around the paper cone or plastic cone. And then there's a basket, which is made of steel or aluminum or magnesium, something stiff to hold all of this in place. This cone comes down to a cylinder. That cylinder happens to have wires wrapped around the cylinder. It's like a toilet tissue roll. Imagine a toilet tissue roll. It's a paper cylinder. And wrapped around, that cylinder is glued onto the end of the cone. And around that cylinder happens to be windings of wire, which we call the coil. That coil is able to move within a space that is formed by a magnet and a pole piece. Depending upon the signals that we deliver to the terminals, these wires to the terminals will go to the coil. And as the signal goes into the wire coil, it will create a magnetic field around that coil of wires. Because it's a coil of wires and it's concentrated, the magnetic field, it will react with the fixed magnetic field of the magnet here, such that at times the coil will be pulled in and other times it will be pushed out, pulled in and pushed out. Well, what's attached to the coil is the paper cylinder. What is attached to the paper cylinder is the cone. And the cone moving back and forth like this is moving air. And as the cone moves air, it creates frequencies that the ear will be able to hear. And here is another illustration showing the cone. And as the cone moves back and forth, this piston action of the cone, it creates sound waves like so. Why does the cone move? Because it's attached to the paper cylinder. And the paper cylinder has wires around the paper cylinder, and the wires are attached through electrical leads to your amplifier through these wires right here. These wires carry the signal to the coil. The coil will change its magnetic field relative to the magnet, and therefore the cone moves back and forth. So this is your construction of the speaker. And how you answer this question is explain how this is done. Principles of electromagnetism and induction. So if I go back to here, electromagnetism occurs when we apply signal to these wires. Applying signal to these wires creates a magnetic field. That is known as induction, electromagnetic induction. And electromagnetism is going to be, that creates an electromagnet is what it does. And electromagnetism occurs when this magnetic field of the wires interacts with the fixed magnetic field of your speaker magnets. And as the magnets attract, the cone will go in. As the magnets oppose, the cone will go out. And this back and forth in and out motion of the cone is what creates sound. So that's kind of the best explanation that we can describe for the answer to that question. That okay for everybody? Then it says, what do you think might happen if someone were to gently tap the cone of one of these speakers? What would the other speaker do in terms of electromagnetism, electromagnetic induction? Explain what is happening. Who would like to have a go with this?
I think if you push on one, the other one's gonna do the same thing.
That would be correct. Tapping one speaker creates a
wave.
Tapping sound out of the other speaker. Now, it will be, creates a lower volume. It won't be the same, okay? But it will be a lower volume out of the other speaker. So that is correct so far. Then that's what the other speaker would do. What would happen? So, okay, what would the other speaker do? All right. So, and explain this in terms of electromagnetism, electromagnetic induction. Tapping first the speaker creates an electromagnetic induction that creates a current in the wire to the other speaker, which will cause the voice coil to react with the fixed magnet of the second speaker, and to produce a sound via electromagnetic induction. So tapping one side will cause the other. By tapping one side, it creates. We're creating a generator, if you will, when we're moving a coil in a field of fixed magnets. So it creates an electromagnet by moving a coil in a fixed magnetic field of the first speaker, which via electromagnetic induction creates a current in the wire to the other speaker, which will cause the voice coil to react with the fixed magnet of the second speaker, to produce a sound via electromagnetic induction. Okay, that's a little more thorough answer there. And then finally for number 11, which magnet moves past the wire will produce the greatest voltmeter indication? So do we move the magnet perpendicular, parallel, or no motion at all?
The first one, I believe.
And so would that be, which descriptor do we use? Perpendicular, parallel, or no motion?
Perpendicular.
Mm-hmm. Perpendicular is correct. Cool. You will get the greatest induction where the wires are moving at right angles, meaning perpendicular to where the wires are moving perpendicular to the magnetic field, or same if the magnetic field is moving at right angles to the wire, is where you're going to get the greatest interaction. Okay.